Welcome back to the Explainer. So, you've probably seen those hyper-realistic images popping up everywhere online and thought, how is that even possible? Well, today, we're diving deep into the powerful architecture that's making it all happen. It really is a question that feels like it's straight out of science fiction, right? But the answer lies in this absolutely revolutionary new technology. It's called the Diffusion Transformer, or DiT for short, and believe me, it is changing the game. So here's our roadmap. We're going to start with the big picture of this new AI. Then we'll break down the two core ideas it's built on. After that, we'll get into the nitty-gritty of its architecture, see how it stacks up against the older methods, and finally, we'll reveal the secret ingredient that really gives it its magic. This new approach is making some serious waves in the world of AI art, design, you name it. So let's get into it. What exactly is it? At its core, the Diffusion Transformer is a brilliant mashup. It takes two of the most powerful techniques we have in machine learning and fuses them together. It literally takes the best of both worlds to create something brand new that's built from the ground up to generate these incredible images. Okay, so to really get what makes a DIT so special, we first have to understand its parents, the two fundamental technologies that it's built from. First up, we have diffusion models. I want you to picture an artist who starts with a block of pure, staticky, random noise, just total chaos. The diffusion model then acts like a sculptor, carefully chipping away at that noise, little by little, until a perfectly clear image emerges. It essentially learns how to perfectly reverse the process of adding noise. And the second key ingredient is the transformer. Now, you might have heard of these from the world of language models like ChatGPT, but they have this superpower called self-attention. What that means is they can look at an entire image all at once and understand how every single part relates to every other part, no matter how far apart they are. And this is a massive leap forward from the older methods. See, traditional models called CNNs would process an image by looking at little tiny patches, kind of like trying to see the world through a tiny window. Transformers, on the other hand, see the whole landscape at once. And that global context is what stops you from getting weird mistakes, like a person accidentally having 3 arms. So, we've got the denoising magic of diffusion and the big picture understanding of transformers. How do we actually put those two things together inside the DIT architecture? Let's take a look. It's actually a pretty elegant 5-step dance. First, the model breaks an image down into a bunch of little puzzle pieces, which we call tokens. Then, it adds noise to them. Now, this is where the magic kicks in. The transformer looks at all these noisy pieces at the same time and figures out the exact pattern of noise that was added. Then it just subtracts that noise and puts the clean puzzle pieces back together to create the final image. And inside that transformer engine, there are a few key parts doing the heavy lifting. You have positional embeddings, which are like a GPS for each puzzle piece, telling the model where it belongs. You have multi-head attention, which is like having a whole team of specialists looking at the image, one for texture, one for color, and so on. And then there's this other thing, adaptive layer norm, which, trust me, is the secret weapon. We'll get back to that in just a bit. You know, the wild thing is, during the entire training process, this hugely complex model has just one simple goal: get ridiculously good at predicting the exact noise that was added to an image. By mastering that one skill, it kind of indirectly learns the entire structure of what a perfect, cleaned image should look like. It's a really brilliant approach. Now, this isn't the very first architecture ever used for diffusion. For years, a model called a UNet was the industry standard. So what makes the Diffusion Transformer such a massive upgrade? Well, when you put them side by side, the difference is just night and day. Where the UNet sees things locally, the DIT sees the entire image globally. Where the UNet kind of struggles to adapt to instructions, the DIT dynamically changes its focus based on what you ask it to do. This makes it way better at handling complex instructions like a really detailed text prompt, and it also scales up to high resolutions much more efficiently. So the bottom line is super clear. When you want to generate really complex, high-quality images that need to make sense as a whole, especially when you're starting from a detailed text prompt, the transformer architecture is just a better tool for the job. It's more flexible, it's more scalable, and it understands context in a much deeper way. Okay, it's time. Let's talk about that secret weapon I mentioned earlier. This is the component that truly unlocks the DIT's amazing ability to follow your instructions to the letter. It's called adaptive layer normalization, or ADA-LN for short. Think of this as the system that takes your instructions, like a text prompt saying, a photorealistic image of an astronaut riding a horse on the moon, and injects that information right into the heart of the transformer at every single step. It's how the model actually knows what it's supposed to be creating. And this is why it is an absolute game changer. Ada-LN is incredibly efficient. It's like having a director on set, constantly whispering instructions and guiding the generation process to make sure it stays perfectly on track with your prompt. It's way more effective than older methods, and it lets the model be super adaptive as it moves from that initial block of noise to the final picture. But here's the truly incredible part: the efficiency. This amazingly powerful guidance system adds only about 15% more computational work to the model. That's a massive boost in creative control for a tiny, tiny increase in cost. And that's huge, because it means we can build more powerful models without needing a supercomputer to run every single one. And they even built in one last really clever trick to make this all work smoothly. When the model first starts training, the Ada-LN layers are basically set to do nothing. They're just invisible. Then, as the model learns, they gradually figure out how to apply the guidance from the prompt. This simple idea makes the whole training process much more stable and helps the model learn faster and more reliably. This jump from local patch-by-patch processing to true global understanding isn't just a small improvement. It's a fundamental shift in how AI sees the world. This new foundation opens up possibilities for generating not just images, but maybe videos or even entire 3D worlds, with a level of creativity and coherence that we're really only just beginning to imagine. It leaves us with a fascinating question. What happens when AI doesn't just see the individual puzzle pieces, but finally understands the entire picture?